Hey, this is going to be my lecture about nuclear chemistry, radiation, and balancing nuclear equations. So in order for this to make sense to you, there are a couple things you have to remember. So the first thing you're going to have to remember, here we go. The atom has protons, neutrons, and electrons. These are the three parts of an atom. In this particular PowerPoint, protons will be blue, neutrons will be red, and electrons will be yellow. The proton number is called the atomic number, and it defines the element type. So everything that has two protons, no matter what else it has, is necessarily a helium, for example. The mass number is the protons plus the neutrons. And the way that we write down particular atoms and their mass numbers and their atomic number is like this. With the mass number on top, atomic number on the bottom, and the element symbol. So for example, a carbon with a mass number of 14 and an atomic number of 6 would be written like this. You might also see it with the 14 and the 6 right on top of each other, but I couldn't do that in PowerPoint when I was making this. Sometimes we also have it in a hyphen notation, where instead of having the mass number and the atomic number, we only give you the mass number. So this same carbon-14 would be written like this, carbon-14, that's the mass number. Now, you don't need to be told the atomic number because you can look at the periodic table. Look for the carbon symbol, and wherever that is, you look in the top and you'll see the atomic number. Carbon is always going to be 6. The definition of carbon is that it has 6 protons. So we don't need it. The first part of this is going to be about radioactive decay, which is the transformation of an atomic nucleus into a lighter one where radiation is released, normally in the form of alpha particles, beta particles, or gamma rays. And if you don't know what that is, that's okay. I will tell you what alpha particles, beta particles, and gamma rays are eventually. But basically, radioactive decay happens when a nucleus emits radiation. So there are 3 kinds of radiation. I don't know if you knew that. It's not just all glowing green energy. There's 3 types. You have alpha particles, which are 2 neutrons and 2 protons clumped together, also helium-4 nuclei, because 2 protons is defined as a helium-4. They have a positive electric charge because of the protons, and they are shielded by, meaning they're blocked by, paper and air. Very easy to shield. Beta particles are the next kind of radiation we're going to learn about. They are electrons, or sometimes positrons, but not in this class. Don't worry about what a positron is. We write them like this, with a 0 on top and a negative 1 on the bottom. So they have 0 mass number and negative 1 atomic number because an electron is a negative charge. It's like the opposite of a proton. So it's negative charge. And you can block it with lead, thin sheets of lead, or wood, rubber. Gamma rays are the highest energy kind of radiation. They're high energy photons. They're just beams. They're not particles at all. Well, photons are kind of like they're kind of like particles, but we'll talk about that later maybe. They have no electric charge at all, and they are only blocked by very thick concrete or thick lead. Gamma rays are hard to stop. So, alpha radiation. This is what happens when something emits alpha radiation. You start with an unstable isotope, and magnesium-19 is not real. You see what just happened? This isotope ripped out 2 protons and 2 neutrons from itself and shot them. So the nucleus loses 2 protons and neutrons, and this thing over here, with this thing over here, that has 2 protons, so it is a helium-4. And then it changes proton number, right? So it's not magnesium anymore, it's something else, it's neon. It lost 2 protons, so the number on the bottom goes down by 2. And it lost 2 neutrons, so the top number goes down by 4. 2 for the protons, 2 for the neutrons. So you end up with something new and smaller plus alpha radiation, or helium-4 nucleus. This is alpha radiation. Beta radiation is a little bit different. You start off with an unstable isotope, like hydrogen-3 actually is beta radiative. Then a nucleus transforms a neutron into a proton. This is weird, because neutrons are neutral and protons are positively charged. So because it creates a positive charge by turning the neutral into a positive, it has to create a negative charge to cancel it out, because a positive and a negative cancel out to 0. So look at this top neutron on the hydrogen-3. It turns into a proton, magically. Now, in order to avoid creating electric charge, which is impossible, it shoots out an electron. So you now have a helium-3 with 2 protons and 1 neutron instead, and an electron. The atomic number will go up by 1 because you gain a proton, but the mass number won't change because you lose a neutron, but then you gain a proton, so they cancel out. We say that electrons have a mass number of 0 because they don't weigh enough, they don't count for the mass number, and an atomic number of negative 1 because of the opposite. They're negative and protons are positive. So gamma radiation is the easiest, I think. You start off with an unstable high energy isotope, fake magnesium-19 again. what happens is it just releases energy. No protons, no neutrons, no electrons, just energy as a gamma ray. So zap. And you end up with the same atom, but low energy. You see, magnesium-19, zap, magnesium-19. It just has lower energy. And a gamma ray. This is the sign for a gamma ray, and it has no mass and no charge. So it doesn't change the mass number or the atomic number. It's the same. We can do an experiment where we put these different types of radiation through an electric field and see what they do. And you will find that alpha radiation curves down towards the negative, beta radiation curves up towards the positive, and gamma radiation does not move. This is part of the way that we know the beta is negative, because negatives are attracted to positives, and it's part of the way we know alpha is positive, because positives are attracted to negatives, opposites attract, and it's how we know gamma is uncharged. So once again, shielding. Alpha radiation is stopped by almost everything. Beta radiation can be stopped by most metals, some wood, thick rubber. It's not actually that dangerous. And then gamma radiation goes through a lot. It will go through thin lead, actually, and can be stopped only by thick lead or thick concrete. So what causes radioactivity? Why do things decay? Well, it's because the atoms are unstable. Only unstable atoms decay. So they can be unstable because they have too much energy, in which case they release gamma radiation, or because their proton-neutron ratio is off. So these are so this is a number of neutrons, number of protons. Things can only exist when they have a particular ratio of protons and neutrons. See this black number in the middle? These black ones? These are the only stable ones. The other ones are not stable. All these possible isotopes undergo radiation because they're not in that little stable line. So if the proton-neutron ratio is off, it'll do alpha or beta decay. So the summary of that is that radioactive nuclides, or isotopes, decay so that they can become more stable. And this is a summary. You have alpha, beta, gamma radiation. Alpha radiation is a helium nucleus with this symbol, and it is very easy to stop. This is an alpha, it's Greek for alpha, and it's positively charged. Beta is an electron, 0 on the top, -1 on the bottom. It has medium penetrating power. This is the Greek beta, and this is a -1. Gamma radiation is pure energy. A photon is another way to call it. This is the symbol, 0 on top, 0 on bottom. It has no charge, right, because it has a 0 on the bottom, and it's hard to stop. So now let's blow right on to nuclear reactions. Whenever you have radioactive decay, you have a nuclear reaction, because the nucleus changes into something else. Now we talk about nuclear reactions, or represent them with nuclear equations. They look like this. And this might seem very daunting, which means scary, and confusing, but it's not that bad. See the way that you have a left and a right side of the arrow? The stuff on the left side of the arrow is what you have before the reaction. So like up here, let me skip back a little bit. Skip. Okay, right here, the hydrogen 3 would be on the left, and the helium 3 and electron would be on the right. Skip through this again. Sorry. Okay, so these are what you have before, and these are what you have after. The arrow is a separator, beginning to the end. Now the stuff we start with at the beginning is called the parent nuclide. The big chunk we make at the end is called the daughter nuclide. And then this right here, this helium, and then this electron, and then this gamma ray, these are just called radiation. So the parent nuclide radioactively decays into the daughter nuclide and the radiation. So this is how we understand nuclear equations. I want you to notice something. These top numbers are going to equal each other. What you have before is the same as what you have after. You don't create mass out of nowhere. You don't destroy it. So the numbers on the left and the right of the arrow will always add up to be the same. Same thing with atomic numbers. The numbers on the left and the right will always add up to be the same, because if you magically create a proton, you also have to create an electron to cancel it out, and that's a positive one and a negative one, and they cancel. So the mass number and atomic number on each side of the arrow will always be the same. We can give you two different kinds of problems with nuclear equations. We can give you equation problems like this, where I have an equation and a question mark, and you have to tell me what it is. Or you can give you, or I can give you a word problem, which is like this: polonium-210 undergoes alpha radiation. What's created? So the equation problems are easier. Let's start with this. First, you have to figure out the missing mass number using algebra. Now you know that whatever the mass number is, 131 equals that number plus 0, because the left and the right side of the arrow have to be equal. So 131 is the mass number, because you subtract 0 from both sides. Then you figure out the atomic number. Similarly, 53 equals something minus 1. And that number has to be 54, because to get rid of a minus 1, you add 1 to both sides. So then, once you know what the mass number and the atomic number are, you look up the symbol that has that atomic number. In this case, it's xenon. And you write the element. That question mark is xenon 131. And then the 54 is the atomic number on the bottom. So word problems are very similar. This is just one extra step. This is it. Polonium-210. Well, you have to figure out what polonium-210 is. So you look up polonium on the periodic table, and you see that polonium has the atomic number 84. So 84 on the bottom, 210 on the top, polonium. Arrow, because you start with polonium-210, and then it alpha decays into something else. And then on the other side, you have to know that the alpha particle is this, 4 on the top, 2 on the bottom, He, the helium nucleus. So you write the alpha particle on the right side of the arrow because you know it alpha decays, and then you figure out what the question mark is. So after you write down the parent nuclide and the type of radiation, you can solve for the daughter nuclide by doing the same process as before. Figure out the mass number. 210 equals something plus 4, so it's 206. Figure out the atomic number, so 84 equals something plus 2, that's 82. You look up the symbol for atomic number 82, which is Pb, lead. And so this is your answer. Lead with a 206 mass and 82 atomic number. And these are all called nuclear transmutation, because transmutation is what happens when an element changes into another element, or an isotope changes into another isotope. When the nucleus changes, you have nuclear transmutation. All of them except for gamma decay are going to involve nuclear transmutation, but it's just important to know what it means. So, some common word problems and a way to understand them. If an element undergoes alpha decay, that means that it loses an alpha particle. That'll be on the right side of the arrow. The mass number goes down by 4, and the atomic number goes down by 2. The element undergoes beta decay. Well, it emits a beta particle, which is a 0, -1 electron. The mass number doesn't change, but the atomic number goes up by 1 because it gains a proton. And if it undergoes gamma decay, it emits a gamma ray, which this is the symbol for. The mass number and the atomic number do not change. You end up with exactly the same atom, just lower energy. We're almost done. Now we've got to talk about fission and fusion. Nuclear fission occurs when you split one nucleus into 2 or more smaller nuclei. Often it requires a neutron collision to start. So a parent nuclide eats a neutron, basically, and then spontaneously breaks down. It releases tons of energy. Here's an example. You have a neutron heading towards a uranium-235. It hits it. Then it spontaneously starts to split. It forms 2 bigger nuclei and some neutrons that move out and are free to collide with other uranium atoms to cause a chain reaction, which is this. You notice that I started by hitting it with a neutron, right? And then I ended with 3 more neutrons. So if these neutrons are around other uranium particles, they will hit them and cause them to blow up. And those uraniums will cause even more uraniums to blow up. And so the material that starts the reaction, you make it as a product and it starts it again. It's a cycle. We can use nuclear power in fission reactors. That's what we currently do right now on Earth. We use nuclear fission to make our power. Fusion would be better, but we can't really do it. This is fusion. You have 2 small nuclei right here, a deuterium and a tritium. Those are 2 isotopes of hydrogen. They combine into a bigger molecule and release a lot of energy. So fusion is better than fission in almost every way. It occurs naturally in stars. It's how the sun makes heat and light. This is the fusion process. So 2 hydrogens come together and they fuse into 1 atom, which is a helium, releasing a neutron and energy, a lot of energy. Fusion reactors would be great, but we can't actually make them. Whenever we try, it's too hard. So these hydrogens, they do not want to be close to each other. They hate each other. So it's very difficult to make them combine into one. You have to squeeze them together very, very tightly. And we can't do that in a sustainable way right now. We do not have fusion reactors. So fission is not great because it requires uranium, which we're going to run out of. There's a danger of a meltdown if it gets too hot. There's toxic waste, and you make a lot of pollution. Fusion is better because you use fuel that you get from the ocean and from the air, just hydrogen. No danger of a meltdown. There's no toxic waste because you only make helium, which is really useful, actually. We could use some more helium. And we can't actually do it yet, which is a downside, except for in bombs. So some uses of nuclear reactions. We use it to see inside you for medicine. We use it to see inside natural processes. We use it to treat cancer, which is ironic because it kind of causes cancer. And we irradiate food, actually. We use gamma radiation to kill bacteria so that your food lasts longer and doesn't make you sick. It's also in smoke detectors. But the big one, of course, is nuclear weapons. So the atomic bomb works by forming a critical mass of uranium-235. Basically, if you put enough uranium-235 together, it will just explode by itself. That's a critical mass. So it creates a critical mass of uranium, and then the fission causes a chain reaction, and it blows up, releasing a lot of heat. A hydrogen bomb is another kind of nuclear weapon, which is more powerful than atomic bombs because we actually use fusion and fission. Remember I told you that we couldn't do fusion on Earth? Well, we can. It just requires such ridiculous conditions that we can only do it in a nuclear reaction, and that's not safe. So you have a chemical explosion, and then fission occurs, then fusion occurs. And the fusion increases the fission rate. Hopefully this is helpful.